Okay, so here's our schedule for today. We have a warm-up on the different types of transports. Let's take a look, and then we'll work on water potential problems, and you'll have some time to do a discussion with your thought partners, hopefully, discussion with your thought partners, and you can review some of your answers to the lab to make sure you're on the same page. Okay, so let's take a look at the types of transport. All right, so here is another, again, amoeba sister drawing, and you can see active transport. There's two types here. We got our passive transport over here. We got our three types. A says, describe the difference between passive transport and active transport. Be sure to include concentration gradient and energy in your answer. Let's see what Mackenzie said here. Passive transport is moving molecules with the concentration gradient. That's good. You can say down the concentration gradient as well. Without energy, active transport is moving molecules against the concentration with the use of energy. Perfect. Okay, I like that. It was very nice. Does anyone have any questions on A? Nice work, Mackenzie. All right, B, identify and briefly describe the two different types of active transport. So we got our active transport and our bulk transport. Okay, let's see, Aaron. Endocytosis brings molecules into a cell. Exocytosis secretes molecules out of a cell. Very good. Both of those, Aaron, are describing bulk transport, right? That was just one example, right? So with bulk transport, we're transporting large particles or large quantities of particles with the use of energy. And you're definitely going to have vesicles involved in that process, either exporting in or exporting out. And here, we also need to describe this one, though. This is another type of active transport, right? That just simple active transport. So let's see if we have, let me refresh my screen. Let's see if we have any more answers here. All right, so protein pumps, good. I like that there's protein pumps involved. Energy is involved as well. Let's see if we have any more. Looks like we're protein pump transports ions against the concentration gradient using ATP. The ATP causes the protein pump to change its shapes, allowing the ions to move through the membrane. Okay, good. All right. That's nice. All right, good job, Michael. All right. And then moving up to our third question here, C, identify and briefly describe the three different types of passive transport. So we got our simple diffusion, our osmosis, and our facilitated diffusion. Let's see, Alfredo. Diffusion is a movement of small nonpolar molecules across the membrane from high to low concentration. Nice work. Facilitated diffusion is diffusion, but the use of transport proteins. Very nice. So that would be for the polar, right? Large polar. And osmosis is the diffusion of water through aquaporons through a selectively permeable membrane as well. Okay, so the movement of water through, I'm going to argue a little bit with this one, Alfredo, because I feel like water can, remember, go directly through the bilayer, right? So that would be osmosis when it goes directly through the bilayer. Is that making sense? When water goes through aquaporons, since that is a type of transport protein, that really would be like facilitated diffusion almost, okay? So if you're defining osmosis, yes, water does go through aquaporons, but I would say the diffusion of water through the selectively permeable membrane, okay? But yes, of course, it can go through those aquaporons, and I'm glad you mentioned those because those are, they tend to be on the AP exam as well, okay? So it looks like we're pretty good here with the stuff that we covered yesterday, which was we covered active transport yesterday, but we also reviewed some of the earlier stuff with passive, okay? Any questions on anything that I might have mentioned? You good there? Okay. There's less stuff in this chapter. Chapter 6 had a lot of stuff to memorize. This chapter has less, less material to memorize, but we got some math in here. We got some stat. So we'll do some standard error of mean with our lab. and standard deviation. And we also have water potential. Okay, so it's a little bit of a different chapter. All right, so let's move on. I'm going to go through a water potential PowerPoint. You don't have any notes to fill out, so you can just sit tight. I did open this up. Where did I put it? Is it here? Yeah, here we go. All right, so let's go through. Water potential is the potential energy that water has. This is not membrane potential. We talked about membrane potential yesterday. This is the potential energy that the cell membrane has because the inside of a cell is negative and the outside of the cell is positive. And remember, that is created by the sodium-potassium pump and the fact that there's a lot of negative ions and leaky sodium ion channels and potassium channels and so on. But this is a little different. So here we see the effects of differences in water potential. To survive, plants must balance water uptake and loss. And this is true for all of us, okay? But plants don't have kidneys, right? So, so water potential is driving the movement of water in a plant, and they have adaptations to help handle that. Osmosis, which is water diffusion through the selectively permeable membrane, is affected by solute concentration and pressure. Now, we didn't talk about pressure yet, okay? So now we have a new component, pressure. Water potential is a measurement that combines the solute concentration and pressure, and it determines the direction of water movement, okay? The movement of water. Water always flows from high water potential to low water potential, okay? So that is really important. So if you opened up this PowerPoint on your own, you might want to highlight that or save this PowerPoint. Well, it should all be in Canvas. You really don't need to save it anywhere, but that's something you want to definitely know. Water is going to go from high water potential, high energy, to low energy, okay? Has anyone been to the Hoover Dam before or any kind of dam? It's pretty impressive. Nobody has gone? I would recommend it. Oh yeah, okay, good. Yeah, I would definitely recommend going. I'm not into like any of that stuff, but I was very impressed. We went to Las Vegas, and then we drove to the Grand Canyon, and then we went to Hoover Dam because it was just like one of those tourist things that we did when I was younger with my family. And I just remember being amazed by this huge wall that humans built to stop the river, right? And I was thinking, oh my gosh, what if like one of those bricks just broke? We would all be dead. There'd be a huge wave. And that's because water wants to go from where there's a lot to where there's less, right? That's just a natural thing. It wants to go where there's lots of energy to where there's less energy until an equilibrium is reached. And so water is going to go from where there's lots of energy to where there's less. Maybe you can picture the Hoover Dam or a dam, that huge massive wall, okay? Here is what happens. The solute potential is proportional to the number of dissolved molecules, because remember, that's what solute is. And pressure potential is the physical pressure on a solution, right? If I had a syringe filled with water, I could put pressure on that syringe and squirt all of you, right? That'd be terrible, but I could do that. And that is me forcing water to move because of pressure. And pressure does exist with plants. There's a negative pressure up at the roots where water is being sucked out of the leaves through the stomata. Okay. There's also a positive pressure in the roots. It's called root pressure. So pressure is a driving force of water movement in plants. The addition of solute reduces water potential. This is confusing to people. And I'll show you the formula where you'll see it's negative ICRT. So as you increase the concentration, C, it's because it's a negative value. It's negative ICRT because it's negative. That will reduce water potential. Hopefully that makes sense. If there's more solutes, there's less water, right? The water will be attracted to the solutes. There's less free water molecules, okay? So it's like a backwards thing, and students struggle with that. So let's take a look. Here we have pure water. Here's our water potential. This little symbol here, this Greek symbol, represents water potential. So water potential equals 0 megapascals, okay? That's just a measurement of that energy. So here you can see pure water has 0 water potential, okay? We good with that? This is an open container. There's no pressure on it. Because of the formula, negative ICRT, there's zero. This is zero molarity. So everything times zero is zero. So that's why water potential is zero. Okay. Over here, I now have a 0.1 molar sucrose solution, or it just says solution, but most of these are involving sucrose. Again, there's no pressure on this side of the tube. And so that's why pressure is zero. And because I do have a solute, when I plug in that formula, negative ICRT, let me show you that formula so you can see it. You have a link on your agenda as well. For some reason, it popped up on this screen. Okay. All right, so when we take a look, I think it's on the bottom of the next page. Here we go. Here it is. Okay. So here's water potential. It's pressure potential plus solute potential. Okay. Water potential will be equal to the solute potential of a solution in an open container because the pressure potential of a solution in an open container is zero. Okay. We're ignoring atmospheric pressure. Solute potential is equal to negative ICRT. I equals the ionization constant. So because sucrose, most of these problems are dealing with sucrose. Because sucrose is not a salt and is not an ion, it's going to be one. It acts as one particle. If this were sodium chloride, NaCl, that would disassociate and act as two particles. So I would be two in that scenario. C is the molar concentration. R is a pressure constant, and there's the units for it. And T is temperature, but it's in Kelvin. So you have to add, you have to make sure it's in Celsius and add 273 to it. And then you just kind of plug it all in, okay? But this is what's confusing, is that negative symbol. So as you're increasing molarity, because that's how we measure concentration, right? Moles per liter. As we increase that molarity, it becomes more and more negative. And again, water has no mole, it's zero molarity. So that's why water's water potential in an open container is zero, okay? Because anything times zero is zero. So there's that formula sheet. Let's go back to this real quick. Okay, so here you can see that the water potential on this side of the tube is negative 0.23 megapascals. This is a selectively permeable membrane that will not allow the solutes through, okay? So therefore, water is drawn to this side because remember, water is going to go from a high water potential to a low water potential. Now, you knew that already, right? I would say this is hypotonic, this is hypertonic, and water goes that way, okay? I'm just adding this concept of water potential to it now, okay? And pressure, because we didn't talk about pressure before, but pressure is important, okay? Especially with plants. Are we good with that? Does that make sense? How water's moving to the hypertonic side because there's a lower water potential there because there's less free energy in the water molecules. There's more here. Zero is larger than negative 0.23. Any questions on that? All right, let's move on to pressure now, physical pressure. Physical pressure can increase water potential because remember it's water potential equals pressure potential plus solute potential. So let's add some physical pressure onto this tube, okay? So here you can see if I have this piston and I'm pushing down, that I can exert enough pressure to stop the water movement. Does that make sense? That I can put enough pressure to stop that water from moving over to that side. Now, how would I have to do that? I have to exert the perfect amount of pressure to make sure the water potential is zero. Because if water potential is zero on both sides, that would be a dynamic equilibrium, okay? And water would move back and forth at equal rates, okay? Does that make sense? How I'm 0, 0 now. All right. I can actually apply even more pressure to force water to the other side. I just have to make sure that my pressure that I put on there is larger, and this ends up being larger than 0, okay? So this really could be any number greater than 0.23. It could have been 0.24, 0.25, right? 0.5, 1, okay? But it would push the water in the opposite direction because remember, water always goes from where there's more energy to where there's less. Just picture that dam, okay? The water behind a dam, how it wants to go to where there's less energy. All right, negative pressure. This is what happens when you suck on a straw or a vacuum. Okay, that creates negative pressure. Negative pressure is not pushing down on something, but pulling up on something. Okay, so here you can see that I can put negative pressure on this side of the tube. I could put it on that side of the tube too, but in this scenario, I'm putting some negative pressure. See how it's negative? Okay. The solute is still 0 because there's nothing in water. And now my water potential on this side happens to be negative 0.3. So I can force water this way because of that. And that is exactly what happens in leaves. The atmosphere is sucking water out, putting negative pressure on the water molecules, pulling the water up the tree, okay? If it's very humid out, there's less negative pressure and water will not leave the tree as rapidly, okay? So here you can see that it's moving that direction because remember, water always goes from high water potential to low water potential. And this number, this is where it gets confusing because it's negative. But this number here is larger than that number there. Okay. All right, you good? All right. All right, water potential affects the uptake and loss of water by plant cells. We're talking about flaccid cells, hypertonic, plasma. Okay, so here you can see that we can predict water's movement with problems. And I don't really want to go into those problems because I have different problems to go into. Okay, so, but if you wanted to go back and you can do this as a practice problem and see how you do with it. Okay. All right, does anyone have any questions on water potential? Remember, this is water's potential energy to move from one place to another, which is really important in plants because water needs to go from the soil to the leaves because that's where it's needed for photosynthesis. And they don't have a pump, right? That would be weird. Plants had a pump, like a heart, to move things around. All right, let's go into some sample water problems. You guys want to click on that? And I actually have, if it is easier for you to do sample problems on a piece of paper, feel free to, okay, right now. You're gonna need a calculator too. If you're okay with just using Cami, that's fine. But if you do a piece of paper, make sure you insert your image, okay? Your image just has to be in a JPEG. Sometimes with your phone, it's not saving it in a JPEG anymore, okay? So I'm gonna stop sharing my screen and move this over here so I can see you folks. All right, there we all are. Let's pin my video. Okay. There. You guys see this okay? All right. So this should be what you see. I just edited this last night because I simplified the problem. So if you talk to students from last year, they might say, oh my God, I hated water potential. And you might be thinking, this is not that bad. And that is because I got rid of the hard water potential problems. I thought, you know what? I haven't seen a hard water potential problem on the AP test in like 10 years. No one has, if there are any water potential, they're very straightforward. So I said, you know what, I'm just getting rid of them. This is a virtual year. It's going to be harder for you folks because, you know, we're all over the computer. So don't be scared of water potential if you talk to anyone from last year. Okay, so let's go through. I have 3 sample problems, 1, 2, and 3, that I'm going to go through. And then you guys have 6 practice problems that you can work with your thought partners on. All right. So please stop me if you're confused. The initial molar concentration of the cytoplasm inside a cell is 2m. That capital M is molarity. The cell is placed in a solution with a concentration of 2.5 molarity, and molarity is equal to moles per liter. So you'll see me sometimes draw that out. All right, so I like to put my beaker, I like to draw it out. I'm a visual learner. So I'm going to draw out my beaker and I'm going to put my cell in there. Okay. So it says the cell is 2 molar. and outside is 2.5 molar. Okay. Now, we're going to ignore pressure because guess what? They're not telling us pressure, right? We can't make up numbers, so we're going to ignore pressure. Anyone want to tell me how you think water will go, ignoring pressure? You know this from before. What's hypertonic? What's hypotonic? What should happen? Where will water go? Remember, this is a selectively permeable membrane, so we're not looking at molarity moving. We're looking, molarity is trapped. The water is going to move. This is osmosis. Zoe.
Water would move outside the cell into the solution because there's a higher molarity outside of the cell than inside the cell. So there's more like water inside the cell.
Perfect. Okay, so we are going to draw, let me make this a little bigger so you can see. All right, so I like to do that right from the beginning so I don't forget what happens, right? Sometimes you end up getting these questions, they get so complicated and you're like, wait, what happened again? So that's why I like to draw it out so I'm not rethinking the same scenario 10 times, okay? So water is going to be drawn out. Now let's go to our water potential. Water is leaving the cell. So where is the high water potential? Where is the low water potential? Remember the Hoover Dam, okay? Can anyone tell me now, where would be more water potential, the cell or the solution? Okay, Gabby.
Inside the cell.
All right, perfect. So now I'm going to point to inside the cell because my cell is a little small, and I'm going to say that inside the cell has high water potential. Okay, and outside the cell has low water potential. Because remember, water goes from high water potential to low, okay? Another thing you can think of is this has more molarity. So this has to have lower water potential because remember, water potential equals pressure potential plus solute potential. And there's a special formula for this, negative ICRT. So as you increase your concentration, you are becoming more negative. And pressure is going to be 0, unless they tell you pressure is 0, okay? You just put a 0 in there. All right, so that's kind of what you need to know before we can start. Does anyone have any questions on that? Again, feel free to draw this out on a piece of paper. You don't have to do it in CAMI if you find that frustrating. And then you can just add a page in your CAMI document and take a picture of this so you have everything in one spot on Canvas. All right, let's read A. Initially, this is a true-false statement, okay? We got to see if this is true or false. Initially, the free energy is greater inside the cell than outside. All right. So here's our initial scenario, okay? Would you agree with that or would you disagree? Free energy? Okay, we don't know what free energy is. Well, that's just energy. That's water potential, right? We said how water potential is water's potential energy. So what would you think with this? Hold up one finger for true and 2 for false. Is this true or false? Okay, good, true, nice, true. All right. B, this cell is in equilibrium with its surroundings. True or false? False, good. Okay, remember isotonic would be in equilibrium, right? 2.5, 2.5, 2, 2. All right, C, initially the solute concentration is greater outside the cell than inside the cell. True or false? True or false? All right, true. Okay, good. Are we okay so far? All right. Water will enter the cell because the solute, oh, wait a minute, I'm not even going to read this anymore. Is water going to enter the cell? Like if I start reading that, I might get confused. This is false, okay? This is false. Okay. And over here we can say, I was supposed to correct this. The solutions are not isotonic. And there is no pressure. Okay. Okay, and so what's wrong with this? Well, water is not entering the cell. Water is going to leave the cell. And you don't even need to worry about that. Water will leave the cell. All right, E. The cell will become flaccid. What does flaccid mean again? Serena.
It means that it's like gonna be like droopy.
Yeah, like, right? Okay. All right. The water will become flaccid. So yes, the cell will become flaccid. Yes, it's going to become flaccid. It might even plasmolicize. Let's keep going. Because the pressure, pressure? We said pressure 0. We don't know pressure. Pressure is not even told to us. That's not why. Okay. It's not because of pressure. It has to do with solute potential. Okay. Not pressure. It has to do with solute. It has to do with water potential, but not pressure. Okay. F. Initially, the cytoplasm is hypertonic. True or false? Initially, the cell, no, that's false. Good. The cytoplasm is hypotonic. Initially, the numerical value of the solute potential is more negative inside the cell than outside. This is where it gets kind of confusing, right? True or false? True or false? More negative would be a smaller number, right? So is it more negative inside the cell? True or false? Hold up, 1 finger or 2? I'm not seeing fingers. 2, yeah, good. That would be false. Okay. It would be more negative outside the cell. Okay, because remember, water potential is going from high to low. Okay, and so it has to be larger in the cell or less negative. Okay, not more negative. That would be a smaller number. The net diffusion of water will be from inside the cell to outside. True or false? Okay, true. Good. And that's why this picture helps, right? You can always go back and look at it. At equilibrium, the molarity of the cytoplasm will have increased. True or false? True or false? All right. The molarity of the cytoplasm should increase. Can anyone tell me why that would be the case? I'm seeing a lot of false. Why would the molarity increase? Even if Cameron?
Is it because there's like less water inside, so the concentration becomes greater?
Exactly, because the solutes are trapped, but water left. Okay, does that make sense? So because water left, but the solutes are trapped, it becomes more concentrated. And I mean, it's going to keep doing this until equilibrium is reached, so it might even get to 2.5. Does that make sense? It's going to go until it's 2.5, 2.5, okay, until it's the same. All right, at equilibrium, the pressure potential, by the way, at equilibrium means after water moved, okay? So if you don't know that, you can jot that down. At equilibrium, it means after water moved, okay? After water moved. At equilibrium, the pressure potential inside the cell will have increased. Do you think this cell is going to have more pressure or less pressure? All right, Grant, I like your thinking it's false. Can you explain?
Because if we're thinking about like with the Hoover Dam, there's more pressure going out, but if the water is released, there'll be less pressure.
Yeah, there's less because there's water leaving, right? So if water was going in, then that would put pressure on the cell. But because water is leaving, this cell has less pressure than what it had before. Does that make sense? Okay. So we are going to say false. The pressure potential inside the cell will decrease because water is leaving. And water is what's putting pressure, okay, on the cell. In your AP video, I keep watching them and I'm mixing them up, so I don't know if it's last night or if it's tonight's, because I always am one day ahead of you guys. I do my homework the day before you guys. So in one of the videos, it talks about where water goes. So when water is drawn into the cell, it goes into the central vacuole in a plant cell, and then that fills up, and then that puts pressure on the cell, okay? So it is the water that's going in or out that's putting pressure on the cell, okay? All right, any questions with that sample problem? Let me see everybody here. All right, I don't see any hands up. Okay, all right, so then let's go back to sample problem number 2. Calculate the water potential of a solution of 0.5 molar sucrose that was kept at room temperature, which is 23 degrees Celsius. Okay, so now we need our formula. Okay, so our formula, and you can look at your formula sheet. I have a link on the home page, but here's our formula. Water potential equals pressure potential plus solute. Now you can switch those around. I forget what the formula sheet has written down. I just kind of, I mean, I guess I could pull it up on another screen. So those are our 2 components. Again, if they're not going to give you pressure, you just kind of put 0 there. So let's see, 0, because there's no pressure told. So we're going to just ignore it. And most of the time, the pressure is 0 because flaccid cells have no pressure. Open containers have no pressure. So this looks like it's a solution. So that would be an open container. So we can point to that and say open containers have no pressure. Okay. Open containers have, this is a solution. It's not a cell. You can't say a cell is an open container. That's weird. It would not work if it were an open container. And then we do have this negative I CRT to solve this piece. Sometimes it's giving you bars, then that's this. But sometimes it's giving you molarity, that's C, okay? That would be C, that's concentration. And it's giving you temperature. Now, sometimes they give you temperature and bars, then you don't need the temperature. They're just giving you extra information, okay? So let's keep going. So we got our 0, so I'm gonna ignore that now. And I'm gonna substitute in -1, okay? This is an ionization constant. If you remember from the formula sheet, it says sucrose has an ionization constant of 1, okay? Because it doesn't ionize, because it is not an ion, it's a molecule, okay? Let me pull up the formula sheet and share with you folks so you can see, just in case you forget. Where's my sharing? There we go, share. Okay. All right, and remember this is on the home page, on the agenda, and it's also in your introductory material if you ever need to kind of get to it. All right, so see where it says 1, just in case you don't trust me there. And now we have C, okay? And then there's our big mess. Now our C is going to be 0.15, okay? Now I'm not going to put capital M. I'm gonna put moles per liter, because with AP, writing out units is a big deal, okay? You get points for units, so you don't wanna forget them, all right? So you'll definitely get points on an essay for these units. So I'm gonna write that out, because trust me, you'll see, it's gonna cross stuff off, and we'll end up with bars. All right, here's our R. It's a crazy big number. It's on our formula sheet. So I'm going to copy it down. 0.0831 liter. Bars is on top. Mole and Kelvin is on bottom. Okay? And this is always the same constant. And then our temperature needs to be in Kelvin. Okay, so over here, can you still see my paper? Shift it a little bit. Okay, over here, I'm going to convert Kelvin. It tells you how to do this. Temperature equals 23 plus 273. Okay, so that would be what? 296 Kelvin. Okay, so over here, I'm going to put 296 K. All right, Now I'm done with this formula sheet, so I'm going to stop sharing so you can see this a little bigger now. Okay. So did you see where I got that big mess from? Okay. So I got my moles per liter, because that's what M means. Molarity means moles per liter. I got this big mess from the formula sheet, and it's always the same. Some of you might even have it memorized by the end of this. And then over here, I have 296 Kelvin. Okay. Because I converted Celsius to Kelvin, and this was on the formula sheet as well. So you don't have to have that memorized. All right, then I just have to multiply through. But I love crossing off units. I don't know why, it makes me excited here. All right, we got our liters, our moles are crossing off, our Kelvin's crossing off, because remember, they're all on top. And then I'm left with bars. And that's how you know you did the problem right. Don't forget your negative symbol. People many times forget their negative symbol. So you just multiply 1 times 0.15 times 0.0831 times 296. And that big mess ends up being, if I did this right, negative 3.69 bars. Don't forget your units, and don't forget your negative symbol, okay? Does that make sense how we did that? And again, pressure is 0 because it's an open container. If this is a cell and they're not telling you pressure, it's 0 because it's a flaccid cell. Any questions on that? Any questions there? Okay, let's see. Let's see hands up. Okay. All right. Oh, you guys are all like in a strip. You're going forever. Okay, so let's look at the last sample problem. A flaccid cell, again, flaccid. You think flaccid, you're thinking that, right? That means that there's no pressure. Okay, so usually there's no pressure. Okay. So let's keep going. A flaccid cell has a solute potential of negative, see how it's in bars? So I don't need this, okay? I don't need this big mess. I only need that big mess if they're giving me molarity, but now they're giving me bars. Contains a water potential of negative 3.69 bars. What will the pressure potential of the cell be? Okay, so let's figure it out. So we got water potential equals pressure potential plus solute. I want to know pressure. I'm solving for X. Okay. They are telling me the water potential is negative. Don't forget your negative. Negative 369 bars. And my solute is negative 6.5 bars. Okay, that's my solute. I'm going to isolate X by adding 6.5 to both sides. And it looks like we do have some pressure, right? Yeah, we do have some pressure. So we're adding, let me make sure I did all this right. Yeah, okay. So we are going to have 2.81 bars. That would be a positive. So you know what? I should change this and get rid of the word flaccid, because since there's pressure, it wouldn't be flaccid. Okay, it would be turgid. I'll just say a cell. Cross that off so you're not confused. A cell has a solute. So again, I changed these problems up this year, and I didn't quite think that one through. Okay, we're good. All right, those are our 3 sample problems. Did I do that right? I'm very tired in the morning. Sometimes you guys catch me doing stuff wrong. Did anybody catch me doing anything wrong? We good here? I think we're good. I think I'm awake enough for water potential. Okay. So this one is a little bit more straightforward. This is just a simple algebra problem. You plug in your numbers and solve. This one is a little bit more complicated. And this is just theoretical. Do you understand the theory behind it? It's not necessarily a word problem. It's really just the theory behind it, okay? Which you'll be tested on. They love water potential, okay? All right, so we have very little time. I wanted you guys to go into your breakout rooms, but we will just, you know, you guys can just turn off your videos for a few minutes. Class is over in 6 minutes. Let's go back and look at our agenda. It's always tough on. Okay. All right, so let me, let's see here. Let's share the screen. All right, and get rid of this. Again, this formula sheet, oh, I had it open 2 times and didn't realize that. Okay, so this formula sheet, I put a link here, but if you ever can't find it, you can go into modules and it's in the introductory material, okay? And you can close, I don't know if you guys know this, but you can close this, like these little tabs, if they're annoying, you can close them so you don't have to scroll so much. Oh, let me change my video. Okay, so, but you know, when you're done with the unit, you can just close that little tabby thing like that. But here in introductory material is the formula sheet. Okay, so if you ever need that, and I forget to put a link, that's where you can find it. All right, so we just have 5 minutes here. Let's look at the agenda. I wanted to do so much. I always do this. All right, so I'm glad I got through the sample problems. I wanted to show you that before the long weekend, so that way you can do some practice with them and I'm not throwing it at you the week, because some people do have problems with it. Problems with the problems. I wanted you guys to work on the practice problems, okay, with your thought partners, but you can just do that over the weekend. Don't forget your dialysis. I'll just give you guys time on Tuesday. I wanted you to check your answers with your partners before we actually crunch the data. So I'll give you some time on Tuesday, I mean, because we don't have school Monday to work on that, okay? So here we go. What is your homework? AP Daily Video 2.8.1, due Monday at 11 p.m. Complete the Dialysis Tubing Lab. I love these videos. I know that they might be kind of like, every day, but I think they're great practice for those questions. These questions are complicated, these AP questions, and so it's nice to see one every day, whether multiple choice or essay. You're seeing these. They're from the AP tests, okay, that they're showing you. So you can get better at doing these problems by seeing them, okay? So I hope that you're getting that practice and you're paying attention and learning the concepts, because I think that they're doing a pretty good job at explaining them too, I like them so far. I like the little, animations that sometimes they use, the little videos that they make. But anyway, that's due Monday, so you have plenty of time to get that done by 11 p.m. And then with your Dialysis Tubing Lab, make sure that you got up to table 2, okay, finished. And then water potential practice problems as well, okay? That's the back of this paper. There are 6 problems there, okay, that I'd like you guys to do. Your mastering will be due Thursday by 11 p.m. and your test is Friday. So if you wanted to start mastering, we covered all the material at this point, you could, okay? So if you have extra time over the weekend, you certainly can do that. All right, now with the Dialysis Tubing Lab, just want to show you. Okay, this is spinning. You are going to, on Tuesday, I'm going to go over the practice problems to see how you did with it. And then I want to do some standard deviation. Okay, so I'm going to give you some time on Tuesday to make sure that you guys have the same answers as your partners here and that you have similar answers here as well. Okay, that you're all on the same page with what's going to happen with these bags. And you also need to hit this link. Okay. Hit that link. You're not doing this. You don't have dialysis tubing at home, right? You're not doing this. So you're going to hit this link and do the lab online. Okay. I'll show you the lab. See, this is what you're doing. And again, I did this lab like 5 times. And it tells you continue, and then you make your solution. I love how the glassware is just bouncing on the counter and it doesn't break. That's quite nice. And it just kind of tells you what to do. You take your beaker, and then it says fill the graduate. And Jossie did this one time too. She thought it was fun. She came in here. What are you doing, Mom? Oh, can I do it? I was like, sure, why not? I love how it just magically fills up. That's kind of nice. And so this is our water, so we don't put any sugar on there. So this is the lab. Okay. What did I do? Okay. Oh. Is it not ready for me to put it down there yet? Okay, there we go. So anyway, you're making your sucrose solutions at first, and then you weigh your bags. And so when you are going through this, here, you don't want to do this lab a gazillion times, okay? Here's where you're going to put what is in the bag and what's in the beaker and the initial mass. Okay, you got to type that in. And then your final mass. And then I just need work for any two problems. Final minus initial over initial times 100. Okay, and that is what I'd like you to get done up to there. You were supposed to do it last night, but if you didn't get it done, you got another extra day because I ran out of time. Okay, so on Tuesday, I'm gonna give you like 10 minutes, like, okay, go through your answers, make sure you have the same stuff, because we are gonna start doing some stat on it, okay? And that's the hard part, is the stat. So I wanna make sure I take some class time to do the stat. Standard deviation, standard error, mean. We're going to do all that in class. Okay, so you don't have to. Most of this lab we're doing in class. There's just a little bit you're doing on your own. Okay, it is 8:50. I talked enough. Do you guys have any questions? We're good. Okay. Enjoy your extra time today. Enjoy your day off on Monday. All right.
Thank you.
And
Thank
bye.
you. Thank you.
Thank
You're
you.
welcome.
Bye. Have a nice weekend.
Thank you. You too. David, you okay?